Okay, we're ready to now talk about the algorithm we kind of hinted at when we were talking about solving systems of linear equations. And the method or algorithm we're going to look at to solve a system is known as Gaussian elimination. And so we want to talk about that process. Gauss, Carl Friedrich Gauss, famous mathematician, and he has his name associated with this method and made extensive use of it. So let's talk about this method. First of all, before we actually go through the whole algorithm, I want to look sort of at the end product and where we're going and what we do with it when we get there, and then we'll come back to the algorithm itself. So we start with, one of the things very important is to get our matrix in what is said to be row echelon form. From now on, I'll just abbreviate that REF, capital REF will be row echelon form. Okay, what does that mean? So matrix, and we talked about augmented matrices already. And so if you remember, like here's some examples of some matrices down here. A row is the horizontal, arrays of numbers going across. So there's 1, 2, 3 rows here. Columns are going down. Okay. So when we say the first non-zero entry in any row is a 1, what do we mean? Going from left to right, as we move from left to right, the first non-zero entry is a 1. Okay, first non-zero entry is 1. So we can have as many zeros as we want, but if we hit a non-zero entry, the first one in the row, it must be a 1. And that 1 is what we call a leading one or a pivot one. Second, the leading ones in any successive row must be to the right of the leading one in the previous row. Okay, so what are we talking about? Successive means one after the other. So if I have the first row and I have a leading one in that first row, the second row, the next leading one has to be to the right of that. Has to be to the right. Okay, and what that gives us is what we call the echelon or stair-step form to the matrix. That's why it's called echelon. And finally, if we have any rows that contain all zeros, right, so that's possible, and we'll see that in this process. You might say, where in the world is that going to come from? Well, it can happen. At any rate, if you get a row of zeros, those have to be grouped together at the bottom of the matrix. So if you have one or more rows of 0, they all have to be at the bottom. Okay, so this is row echelon form. Now further, a matrix is said to be in reduced row echelon form. So the reduced form, and this is the abbreviation for that RREF, so reduced row echelon form, that means we have these three things. It's in row echelon form, so reduced row echelon form is a row echelon form. And further, each column that contains a leading one has zeros everywhere else. Automatically in the row echelon form, these leading ones will have zeros beneath them. They will automatically have zeros beneath them if all three of these things are true, because successive rows, the leading one in the next row has to be to the right. So that means directly underneath this one has to be a 0, because the first non-zero entry in any row is a 1. So we always have zeros beneath them, but the reduced form has zeros above the leading ones as well. Okay, so let's just see if we can classify matrices as one of these three things as being in row echelon form only, and by that I mean in a row echelon form, but it's not reduced. In reduced row echelon form, which is a row echelon form, but in particular reduced, or not in a row echelon form. Okay, so let's take a look at this. Is this matrix here in row echelon form? Answer, no. First of all, number 1 is true. The first non-zero entry in any one that I hit is the first non-zero entry in any row is a 1, right? Hit a 1 there, hit a 1 there, hit a 1 there. But the leading one in successive rows are not to the right. In particular, going from the second to the third row, there's a leading 1. All right, so I'm going to circle these leading ones. Here's 1, here's 1, and this one in the third row has to be further to the right. So this is not row echelon form. It's pretty easy. Okay. This one, let's see, do we have a leading 1 in each row? Here's our first leading 1. First non-zero entry is right here. Is that a 1? Yes. First non-zero entry there, is that a 1? Yes. Okay. So there we have 3 leading 1s, and they are in echelon form. Notice the successive going from 1 to 2. Here's leading 1 here. It's further to the right. It's not here, but it's over here. That's fine. It just has to be further to the right. It can be in this, if we have a leading 1 in the first column of the first row, then the leading 1 in the second row has to be in the second, third, or fourth column. Okay, so we're okay, as long as there's all zeros and the first non-zero entry is a 1. Okay, We're on echelon form, and we don't have a row of all zeros. So this is certainly row echelon form. Is it reduced? Remember, reduced says that the leading ones have zeros in all the other entries for the column that it's in. So notice if I go to this leading one here, it's got a zero beneath it. Like I said, this will always be true for row echelon form. However, above it, there is not a zero. There's a -2. Same with this leading one. It has a zero here, but it has a +5 here. So these are not both zero. Therefore, this is row echelon form only. It's not reduced. Okay. This one here, got a leading one here. Let's circle that, leading one here. Here, oh, there's no non-zero entry. No leading one, that's fine. All right, we're in echelon form, and the row of all zeros is at the bottom. Right, so we're good with that. So this is certainly row echelon form. Is it reduced? Well, look at the leading ones. Are there zeros everywhere else in their column? There sure is. So this is reduced row echelon form. Going here, leading one, row of all zeros. It's certainly row echelon form, and since the only other entry in this column where the leading one is, the only leading one is a zero, this is actually reduced row echelon form. Okay. What about this one? Here's first entry is leading one. Here first entry is, that is not a 1. This has to be a 1, right? And so this is not row echelon form. Okay, so just a quick review on that. So one thing to note, that we said the row echelon form, have these three things, and reduced row echelon form is a special particular type of row echelon form. But in any row echelon form, reduced or otherwise, then the location of the leading ones will always be the same position. You might say, what do we mean by different row echelon forms? Well, it turns out, remember, we talked about the 3 elementary row operations that we can do to a matrix, to an augmented matrix we're thinking of, corresponding to a system of linear equations. But we can do row operations, right? And so doing those row operations, we can transform a matrix into its row echelon form, and we can also change one row echelon form to another. Okay, I don't know, in particular, for instance, if I look at this row echelon form, if I were to add 2 times row 2 to row 1, okay, what would happen? 1 plus 0 is 0, 3 plus 0 is 0. 2 times 1 is 2, so -2 plus 2 would be 0. This would become 0 here. 5 plus 0 is 0. The only thing that would be different is this -2 would become a 0. Well, that matrix is still in row echelon form. Okay? Still not reduced. We do have a 0 above this leading one. We don't have a 0 above, all zeros above this leading one. But again, it's a row echelon form. But the key is these leading ones remain in those locations. Okay. Now, going back to, we're thinking about the augmented matrix that comes from a system of linear equations. For augmented matrices, the variables that correspond to the leading ones in any row echelon form are called the leading variables or fixed variables. The remaining variables that are not fixed, therefore, are called free variables. Okay, so if I look up in here, if this was coming from a system of equations, what would we have? We'd have 1, 2, 3 rows, so that would be 3 equations. I have 1, 2, 3, 4 columns. So I have 3 unknowns. Remember, this last column is the constants. So like the first equation would be 1x plus 3y minus 2z equals 5. Okay, so this is the x variables, for instance, this is the y variables, this is the z variables, or x of 1 variables, x of 2 variables, x of 3 variables. Okay. Since I have leading ones in the x of 1 variable column and a leading one in x of 3, then x of 1 and x of 3 are fixed variables. X of 2 does not have a leading one in this column, and therefore it is a free variable. Okay. Now, when we have free variables like we would have in this situation, for a consistent system, what's a consistent system? It's one where there's a solution. Remember, we could have a case where there's no solution. So if it's consistent, meaning there is either, one solution or infinitely many, then the system will have, in this case, infinitely many solutions. So if we know we have a free variable for a consistent system, that's when we know we have infinitely many solutions. And in this case, of course, we're going to write the solution using parametric equations. So let's look at an example here. Here's a row echelon form for an augmented matrix down here. Notice that there's 4 rows. We do have a couple rows of all zeros, but still, we have 4 rows, so that means the original system had 4 equations. Okay, you might say, well, how do you get these zeros here? Well, it's in the process of the algorithm. But the original system had 4 equations. And then how many unknowns are there? There's 1, 2, 3, 4, 5 columns. This last column's for the constants. So there's 4 variables, 4 equations, 4 unknowns. And let me circle the leading ones, right? Here's a leading one, and here's a leading one. Okay, the leading ones in the 3rd or 4th rows. And so it's not reduced row echelon form, but it's row echelon form. Okay, but the thing is, these 2 columns correspond to, let's say, variables x1 and x3. So x1 and x3 are going to be your fixed variables. And that leaves what? x2 and x4 are your free variables. And we'll see in a minute how we write out the solution in the different cases. So our goal is, in the algorithms we're going to look at, is to, by row operations, right, take the augmented matrix for a system of linear equations and get it into a row echelon form. Okay, Gaussian elimination, we're going to be going to a row echelon form. Gauss-Jordan, we're going to talk about a variation of Gaussian elimination known as Gauss-Jordan. There's an engineer by the name of Jordan who gets his name in the mix. Gauss-Jordan method will bring it actually down to the reduced row echelon form. Okay, but let's just see what happens at the end of this algorithm, and then we'll look at the algorithm. In each case, we have a row echelon form for an augmented matrix of a system of linear equations. I want you to give me the number of equations, number of unknowns, and the solution, if any. So by if any, I mean, otherwise you write no solution. And then if it's infinitely many solutions, we're going to parameterize. Okay. So looking here, I have 1, 2, 3 rows. So that means 3 equations. Okay. I have 4 columns. Remember, the last column is for constants. So there's 3 unknowns. And the unknowns are then referred to maybe x sub 1, x sub 2, x sub 3. These are the constants. So these are the coefficients of x sub 1, coefficients of x sub 2, coefficients of x sub 3. And the solution is pretty clear. 1x sub 1 plus 0x sub 2 plus 0x sub 3 equals -5. X sub 2 equals 8. And the third equation, x sub 3 equals 0. So if we want to write this as an ordered triple, right, in order, x sub 1, x sub 2, x sub 3, there's our solution in this case, exactly one solution. Okay, so that's easy. If I can get my augmented matrix to be in this form, then there's the solution. This situation have the same size. I have 3 rows and 4 columns, so I still have 3 equations and still 4 unknowns. This time, notice the row echelon form. I have leading one here in row 1 and row 2, but I don't have a leading one here. Notice the middle variable here, x sub 1, x sub 2, x sub 3, so x sub 2 is free. And I know the system is consistent. The reason I know it's consistent is it's going to be inconsistent if you have a contradiction, like 0 equals 1. This last equation says 0 equals 0. That's not a contradiction. Here I've got x sub 3 equals 8, and then an equation involving x sub 1 and x sub 2. So this is a consistent system. Okay, but in this case I have infinitely many solutions, so I'm going to parameterize, and I'm going to let the free variable be the parameter, and that's what you want to do. Free variables always become the parameter. Free variables always become the parameter. Okay, so x sub 2 is t. What's the second equation say? It says, as I said, x sub 3 equals 8. 0 x sub 1 plus 0 x sub 2 plus 1 x sub 3 equals 8. So there's x sub 3 is 8. And then this equation here tells me what? 1x sub 1 plus 2x sub 2 plus 0x sub 3 equals 4. So I've got this equation. But remember, x sub 2 is t. And so right? Replace that with 2. So I get x of 1 equals 4 minus 2, x of 2, or 2t. All right, solving for x of 1. So x of 1 is a fixed variable, x of 3 is a fixed variable. We can solve for that. X of 2 is a free variable, it's assigned a parameter. So what's our solution? X of 1, which is 4 minus 2t, x of 2, t, x of 3 is 8. Infinitely many solutions of this form. T is the parameter. Choose t to be any real number, and then we have a solution. Again, a system with 3 rows, so three equations, 4 columns. Remember, the last one's the constants, so 3 unknowns, so that's the same as the previous 2. And this time, again, I have leading ones here, here, and here, right? But let's just jump to this last one. This should stand out. What's this last equation say? 0x1, 0x2 plus 0x3 equals 1. This says 0 equals 1. That's a contradiction, right? It's a contradiction. And what does that tell us when we're looking for the solution to the system? It tells us that there is no solution. So that's what you would write. What is the solution? No solution. There's no value of the variables that would solve for all 3, that would satisfy all 3 equations from the original system. So anytime you have all zeros and then a 1 at the end in any of your row echelon forms, you'll know right away that's a contradiction. This has 2 rows, so 2 equations. It has 5 columns, 1, 2, 3, 4, 5. Last one being constant, so there's 4 unknowns. Okay. And I've got leading ones here and here. Those are my fixed variables corresponding, right? So I've got x of 1, this time x of 2, x of 3, x of 4, and, oops, no, just x of 4. Sorry, that's constants. Just the constants there. So I've got, I said 4 unknowns. And I know it's consistent. It's not. There's no contradiction, right? So it's no situation where I have no solution, because I don't have 0, 0, 0, and then a 1 in the last column anywhere. So I do have infinitely many solutions, and my free variables, x of 2 and x of 4, are my free variables, and so they become parameters. So maybe I let x of 2 equal r and x of 4 equal t. Again, what you choose for your parameters can vary from what I have here. You can use S, U, V, W. Those are common letters that we use for parameters toward the end of the alphabet, excluding X, Y, and Z, because those are usually variables. Okay, and then I have let's go with the first equation. What's that say? 1x1 minus 3x2 plus 0x3 plus 5x4 equals 0, right? But I can solve this for x of 1 by adding 3x of 2 and subtracting 5x of 4. But then write x of 2 is r and x of 4 is t, so I can write x of 1 in terms of my parameters. 3r minus 5t. The second equation says 0x of 1, 0x of 2 plus 1x of 3 minus 1x of 4, so minus x of 4, equaling 6, and therefore I can solve for x of 3, the fixed variable, by adding x of 4, So 6 plus x of 4, but x of 4 is t, so this becomes 6 plus t, or t plus 6. And so there's x of 3, there's x of 1, x of 2, x of 4, so we can now give the solution. It is x of 1, 3r minus 5t, x of 2, r, x of 3, 6 plus t, and x of 4, t. Infinitely many solutions in this case. So I want us to thoroughly understand what's going on here. I like questions like this. This is, when we get to the end, do we know how to give the solution? Another way to sort of look at this is to go in the other direction, and that is give information about the solution and ask for the corresponding a possible row echelon form or reduced row echelon form for the original system. So in each case now we're going to go in the other direction, so to speak. Write out a possible reduced row echelon form of the augmented matrix for the system described. Okay, so let's see how we do this. 3 equations. That tells me immediately that my matrix will have 3 rows. So sort of going back in the other direction. 3 unknowns. What's that tell me about columns? There's 4 columns. You say 4, what about the 3? Well, there's 3 unknowns plus what? The constants, right? And so I've got a total of 4 columns. And basically this one's pretty easy. I have just one solution, x1 equals 4. So that's going to tell me my first row in my augmented matrix in reduced form will be what? 1x1. How many x sub 2's? 0. How many x sub 3's? 0. Remember there's 3 unknowns. X sub 1, x sub 2, x sub 3. Right? Equals what? Equals 4. There's my first equation, or my first row. The second is x sub 2 equals negative 3. That tells me 0x sub 1, 1x sub 2, 0x sub 3 equals negative 3. X sub 3 equals 0. 0x sub 1, 0x sub 2, 1x sub 3 equals 0. This right here is your, notice this in reduced row echelon form as well, right? I've got leading ones in each row in this case. They're in echelon form, and it's reduced because all in the columns with the leading ones, every other entry is a 0. So there's going it sort of in reverse. What happens if we have, again, 3 equations, which is 3 rows, and 3 unknowns? Again, 4 columns, so same size as the previous one. But this time the solution, notice there's a parameter in there. X sub 3 is a parameter. How is that going to affect things? Okay. Well, what you want to do here is sort of work backwards. Right? X sub 3 is t, so I want to plug in t for x sub 3. So x sub 1 is what? 3 minus t, but t is x sub 3. And then add the x sub 3 back. This is sort of just the opposite of what we were doing when we were going in the other direction. And this gives me my first equation. 1x sub 1, or first row. 1x sub 1 plus 0x sub 2 plus 1x sub 3 equals 3. There's my first row, or my first of the 3 rows. Okay, from this right here. This one, x sub 2 equals 1 plus 5t, but t is x sub 3. And here I can subtract the 5x sub 3 to get it in this form, x sub 2 minus 5x sub 3 equals 1. So here's my second equation, and so the second row is what? 0x sub 1, 1x sub 2, minus 5x sub 3 equals 1. Okay, well, I've got my third row right now. What's my third row going to be? Well, do x sub 3 equal t. Does that give me an equation? X sub 3 equal t? No. Remember what that tells me? It means there's no leading one in that third column. Okay, and so what has to, clearly I have to have a 0 here, right? Clearly I have to have a 0 here. It has to be reduced row echelon form. I can't have a leading one here, so what does it have to be? A 0. And then can I have a leading one here? No. I mean, that would tell me no solution, right? Zeros and then a 1. So all of these have to be 0 in this case. Right? If I had a 1 here, then this would say 0 equals 1, no solution. And there is a solution. There's infinitely many. So this has to happen. And notice again, my leading ones are in the first column and the second column corresponding to my fixed variables x sub 1 and x sub 2. There's no leading one in my x sub 3 column, and so that is a free variable and would become the parameter. So again, working backwards, this is the corresponding reduced row echelon form. What would a reduced row echelon form look like for 3 equations again? So that's again 3 rows. But this time 2 unknowns, so how many columns? 3 columns, right? The 2 unknowns, coefficients, and then the constants. But no solution, right? Well, we know what has to happen for no solution. We have to have 0, 0, 0, and then a 1 in the last column. So one possibility is 3 rows, 3 equations. Is at the bottom here I have 0, 0, and 1, right? That tells me no solution. Okay. what has to be up here? Well, clearly, I can have a leading one here and zeros underneath it, right? So it has to be, remember, in reduced row echelon form, right? So that means for the leading one here, I have to have zeros everywhere else. Then I can have a leading one here, I have to have zeros everywhere else. And notice this also is a leading one, right? So this is a leading one, this is a leading one, this is a leading one. So if it's a reduced form, these have to be zeros as well. So this is one possibility. This is one possibility. Or here's another possibility. So I'm asking for only a possible one, so this would be fine if you just wrote that. But I'm also going to look at this situation. I could have in the second row, I could have this 0 equal 1 situation. Of course, this is a leading one, right? So it has to have zeros everywhere else. And clearly, if this is a leading one, any leading one in this last row has to be to the right of that leading one above it. And we can't. There's nothing here. So these all have to be zeros. Okay. What has to happen here? Well, I can't have all zeros in this column. And the reason I can't is this is coming from a system of linear equations. If everything was 0, that means there never was the variable x of 1 in the original system at all. So we do have to have a leading one here. Right? What about here? What do we have to have? Well, again, it can't be 0. I can't have all zeros in this second column. I can have all zeros in the last column, but not in any of these, because again, that would mean there's no x of 2. So whatever this is, let's just put a little asterisk here. This has to be, asterisk is any non-zero number that you want it to be. Okay. So again, if I'm asking you to do this, you don't have to do every case. You just give me one case. This, or you do this and put a 1 here and a 2 here and a 0, everything else. That's the only thing that's variable. As long as it's any non-zero number, that would be another possibility. Okay. So these are the only two real possibilities, given that you are starting with an actual system of linear equations. Okay, one more, and then we'll stop the video, and then in the next video we'll actually look at the algorithm, the Gaussian and Gauss-Jordan elimination algorithms. So the last one is, let's draw the reduced row echelon form of the augmented matrix of a system that is homogeneous. What's that mean? Two equations, right? So that means two rows, two unknowns. That means three columns, right? Because we've got the two unknowns plus the constants. And it has infinitely many solutions, okay? What's that mean? I can't have the situation I had here with 0, 0, and a 1 at the end, right? Which means no solution. Can't have that. And infinitely many solutions, we have to have what? At least one parameter, at least one free variable. So we have to be missing a leading one in one of those columns corresponding to the variables. In this case, we only have two of them. And then what's homogeneous? Well, let's see. First of all, two rows, 1, 2, and then 1, 2, 3 columns. Let's just space. Homogeneous, that part means what? That the constants are all 0. The constants have to be 0. That's what a homogeneous means. The constants are all 0. So make sure you know homogeneous, we talked about that in the last video, is a system of linear equations where the constants are all 0. So that makes it easy there. So I only have one, these two columns in here to do. Okay, so I have to have a leading one here. All right, because again, I have to have a non-zero entry somewhere in this first column. Otherwise, there was no, x1 variables, or the first, we have two variables, x1 and x2. And since it's reduced, this has to be a 0, right? Since it's row echelon form. Okay, then I've got a leading one right here for x of 1. Remember what I said? There's infinitely many solutions, right? So we need a parameter. We need a free variable. Well, x of 1 is not a free variable. It is fixed because of the leading one. That means x of 2 right here cannot have a leading one. Cannot have a leading one. Okay, so that means I can't have a leading one here. So what do I have to have here? I have to have 0 here. Okay, what about here? Well, can this be 0? Well, no. Again, I can't have both of these being 0. Again, this is going to be what? This little asterisk will be any non-zero number will work. Right? Because again, if this was 0, That means the original system can't have possibly had any x sub 2 in them, and we wouldn't have two unknowns. It would be stupid, right? We wouldn't have but one unknown. So this is what it would look like. Again, you don't have to give all of them. You can do like 1, 1, 0, and then all zeros. That would be an example of an augmented matrix in this situation. Okay, so you might need to rewatch that a little bit and retry it. There are some homework problems like this in our first homework set and some in the textbook. So play around with that and make sure that makes sense. We will now, in the next part of this lecture, look at the actual Gaussian elimination algorithm.